Hi, welcome to Introductory Statistics. This is Math 125. We're going to talk about the binomial formula this week. We'll cover chapter 15 from our textbook. So here's the question. In fact, we really have only one question from this lecture that we like to answer, and it takes on this following form. Suppose I perform an experiment like tossing the coin 4 times, and I want to find the chance of getting exactly one head out of the 4 times that I tossed the coin. Or maybe I roll a die 10 times, I want to find the chance that I get exactly 3 aces. Or I have a box containing 1 red marble and 9 green marbles, and I want to pick 5 marbles from that box with replacement. I want to know what's the chance of getting exactly 2 draws that are red. And so all these questions, right, notice have that keyword exactly in common. We want to find that probably that something will happen exactly a certain number of times, and so that's exactly the question that we're going to answer in this lecture. So let's do a simple example. We have a box that contains 1 red marble and 9 green ones, and we're going to pick 5 marbles at random with replacement, meaning that every time I pick it, I put it back. What's the chance of getting exactly 2 draws that will be red? The problem is to find the chance of getting 2 reds, exactly 2 reds, no more, no less, in 5 draws from the box. And so the other 3 draws must be green. So one way that this can happen is that you get the first 2 draws are red and the final 3 are green. So you can write it like this. So again, we're picking 5. And to get exactly 2 red, one way is to get 2 red in the first 2 draw, and then 3 green in the last 3. Of course, there's actually many other ways to get 2 red. For example, here's another one. Maybe you get a red the second time you pick, and then the last time you pick, and then the rest are green. And so to solve this problem, we had to find all the ways of getting 2 red, and we had to calculate the chance of each of them, and we have to use the addition rule to add up all those chances. And so the first task is a little bit tricky to find all the possible ways of getting 2 reds. And so we're going to postpone that for a moment and then look at the second problem. Suppose that I want to find the probability that I get exactly 2 red that is in this exact pattern. In other words, I want to get a red, a green, a green, a green in that order. Well, the chance of getting a red in the first one is 1 out of 10, because again we have 10 marbles, and because these are independent, because we're replacing the marble each time, the chance of getting a red the second time is also 1 out of 10. And then the chance of getting a green one in the third time I pick, again there's 10 marbles, 9 of them are green, so the chance of getting a green is 9 out of 10. And then the last 2 green, same thing. These are all independent, and so all the chances to get a red you get 1 out of 10, to get a green you get 9 out of 10. And so to get exactly this pattern, you have to multiply them, because this is getting a red and a green and a green and a green, and because they're independent, we simply multiply the probabilities. So that means that this is the multiplication rule, and so that's how you find the probability of getting this exact pattern. To find the probability of getting this exact pattern, a green, a red, a green, a green, a red, is actually the same thing, which is switching the order of the multiplication, but we get this exact same answer for any of these patterns where you have 2 red and 3 green. And then if you permute them in different ways, that probability of getting that pattern is always the same: 1/10 to the second power times 9/10 to the third power. And so let's look at these 2 probabilities, A and B. And both of them have 2 red and 3 green, but they're in different orders. And so to get the probability of getting an A or a B, because these are mutually exclusive, if I have A, I cannot have B. If I have B, I cannot get A. So to get a probability of A or B, we just add them, P of A plus P of B. And that's from one of the previous lecture. So that means we add these 2 probabilities together. So this is for getting those 2 exact patterns. Now to find the chance that exactly 2 draws will be red, that means we have to find all the ways to arrange the 2 letter R's and the 3 greens, and then multiply that by the number 1/10 to the second power, and 9/10 to the third power. Because each of those pattern of 2 red and 3 green is this probability of 1/10 to the second power, 9/10 to the third power. And if we permute them different ways, we always get that same probability. To get all the ways of getting 2 red, we have to add up all these numbers. Therefore, we multiply this number by the number of ways of rearranging 3 reds and 3 greens, 2 reds and 3 greens. So again, what we notice is that the pattern green or red, green, green, red has the same chance as the pattern red, red, green, green, green. In fact, each pattern with 2 red and 3 green has the same exact chance. And since the 2 red contribute 1/10 to the second power and to the product, and the 3 green contribute 9/10 to the third power, the sum of the chances of all the patterns therefore equals the number of patterns times the common chance. Again, we add up all these. If we find all the ways of getting 2 red and 3 greens in different order, we basically multiply that number by this probability of 1/10 to the second power, 9/10 to the third power. So the binomial formula allows us to compute the number of the total number of different patterns with 2 red and 3 greens. We'll see this formula in the next slide. But if I were to, by using it, we can actually now compute this problem. It turns out that by using that formula that I'll show you in a second, we're going to find out that there's 10 different ways to get 2 reds and 3 greens. So that means the chance of drawing exactly 2 red is 10 times this probability, 1/10 to the second power and 9/10 to the third power. So again, the 10 is because there are 10 ways to arrange 2 red and 3 greens, and then the probability next to the 10, the 1/10 to the second power, 9/10 to the third power, is the chance of getting one of those pattern of getting 2 red and 3 greens. So you multiply, because we're adding it 10 times, we basically multiply this number by 10. So that means that the chance of getting exactly 2 red is about 7%. Yeah, so that's basically the motivation for this next formula. So given n objects consisting of k objects of the same type and another n minus k objects of a different type, the number of ways to arrange them is this formula. Again, this looks complicated, but we're going to see how this is actually very simple. So let me kind of say this again. So if I have n objects consisting of k objects of one type and another n minus k of another type, so the way to think about that is look back at the previous example. My n in the previous example is 10 marbles. I have 10 marbles in the box. K of them are of one type and n minus k of different type. In fact, that example, k was 1, so 1 of them was red, and then 10 minus 1 was 9 of them was green. So remember, k and n minus k add up to n. So that means in the previous problem, I have 10 objects, 1 of them is red, 9 of them is green. And so this says that the number of ways to arrange that is n factorial times divided by k factorial times n minus k factorial. So this exclamation is the factorial. So 0 factorial is by convention just 1 to make things simple. 1 factorial is also 1. 2 factorial is 1 times 2, which is 2. 3 factorial is 1 times 2 times 3, which is 6. 4 factorial is 1 times 2 times 3 times 4. So we just multiply from 1 up to that number. And so the way we use this formula is that to find the number of ways of arranging 2 red and 3 green, the problem we've been trying to do so far, is we put 5 factorial on top, because that's the total number of objects. And then we put a 2 factorial at the bottom, because k is 2 in this case, and then n minus k is 3 in this case. And so if we I guess so that means earlier I made a mistake of saying that n was earlier. So let's go back on top here. So the n and the k and the n minus k. So n should have been 5 because we have 5 objects that we need to arrange, and then k would be 2 because we have two of them are red, and then n minus k would be 3 because the 3 of them was green. So yeah, sorry about that. I mean, again, this is the same thing. I mean, I think I mentioned the wrong example earlier, but okay. So 5 factorial divided by 2 factorial times 3 factorial. You can do this simple. Again, you can use a calculator, or if not, you can do it by hand by writing out 5 factorial and writing out 2 and 3 factorial, and then canceling a lot of them out, and to get 10. So that means that we have 10 ways of arranging 2 red and 3 green. How about the number of ways of arranging 4 red and 1 green in a row? Well, again, the formula is 5 factorial divided by 4 factorial times 1 factorial. So the bottom is the 4 and the 1. And then again, I can cancel and get 5. So there's 5 ways to arrange 4 red and 1 green. In fact, we can list them out. Here are the 5 ways of arranging 4 red and 1 green. So this formula tells us how many ways to arrange those letters. The number of different ways of arranging 5 reds and 0 green in a row is 5 factorial divided by 5 factorial and 0 factorial. Notice 0 factorial was 1, so if I do this out, I get 1. And that makes sense because if I have 5 red and no green, there's only one way to arrange 5 red. Well, just 5 red in a row. Okay, so here's the binomial formula. It says that the chance of an event that will occur, the chance that an event will occur exactly k times out of n is given by this formula. Where the first part of it is the factorial part. That tells you how many ways we can arrange k objects of one type and n minus k of another type, and then the probability of p to the k and 1 minus p to the n minus k. That's the probability that we saw earlier in that previous example. Where again, the reason why it's p to the k is because p is going to happen k times. P is the chance that some event will happen, and then 1 minus p is the chance that that event will not happen, and so we need to raise that to the n minus k. And the key here is that the exponent k and n minus k add up to n. So I think that this formula is confusing, but if we do some example, it will make more sense. Let's do some example. So let's say we would roll a die 10 times. We want to find the chance of getting exactly 2 aces. So let's see what are all these variables. So in this case, the number of trials is 10, so n is 10. And then we were interested in rolling an ace. So that's basically what p is. So the probability of getting an ace when we roll a die is 1 out of 6. So p is 1 out of 6. P is the event that we're interested in, which is getting an ace. These tries are independent, so that means the binomial formula can be used, and the answer is simply applying the formula. This formula right here. So what is n? N is 10. K, well, k is when we do this 10 times, we need to get exactly 2 aces. So k is 2, and then n minus k is 8. So n is 10. 10 minus 2 is 8. So again, 10 is n. K is 2 because we want to get 2 aces, and then because the probability of getting an ace is 1 out of 6, we need to raise 1 over 6 to the second power because we want 2 aces. And then the probability of not getting an ace is 5 out of 6, so that's the 1 minus p part. And because we get exactly 2 aces, the other 8 times we must get something that's not an ace. That's why it's 5 out of 6 to the 8 power. So again, 1 out of 6 is the p, 5 out of 6 is the 1 minus p. We want 2 aces, so we want 1 to the 6 to the second power. We want 8 not aces, so that's why it's 5 out of 6 because it's the opposite of 1 out of 6, and raise that to the 8 power. So this formula, if you decompose it, it's actually not too bad. You get about the 29% chance of getting 2 aces if you roll a die 10 times. Let's do some more example. Suppose we have a box of tickets as shown on the right. We pick 9 tickets with replacement. Again, we pick 9 each time we replace the ticket. That's why we allowed it. We can pick 9 because we always replace the ticket. Find the chance of getting exactly 2 of them as ones. So again, we just gotta find out one thing at a time. N is 9 because we're picking 9 tickets. The probability of getting a 1, notice, is 2 out of 6. So that means my p is 2 out of 6, which is 1 out of 3, 1/3. And 1 minus p is 2/3. So applying the formula, so 9 factorial divided by 7 factorial and 2 factorial. The 7 is basically getting well, the 2 is getting the 2 ones. The 7 is getting 7 that are not ones. So again, I'm picking 9. I want 2 of them to be ones, 7 of them to be not ones. That's why we have the 9 factorial on top, the 7 factorial, and the 2 factorial on the bottom. And then the chance of getting a 1 is 1 out of 3, but we need 2 of them to be 1, so it's 1/3 to the second power. And then the 2/3 is getting something that's not a 1. We want that to occur 7 times, so raise that to the 7th power. So again, all these numbers are actually not too bad to figure out. You get that 23.4%. So this is the sometimes people say that use this notation for the binomial coefficient. The parentheses, sometimes called n choose k. So make sure you learn how to do this either by calculator or by hand, and then doing that cancellation trick that we saw earlier. So in some calculator you have this n choose k function. If you have that on calculator, that can be helpful, but if not, doing it by hand, cancelling, and then using the calculator can also be pretty fast. Okay, so let's do one more problem. If I roll a die 7 times, now I want to do something slightly different. What's the chance of getting at least 1 ace? Notice it's not exactly 1 ace, but at least 1 ace. So that's different than the previous problem. So how do I do the at least problem? Well, to get at least 1 ace, and I roll a die 7 times, I need to get exactly 1 ace, plus exactly 2 aces, plus exactly 3 aces, all the way up to 7 aces. And these are all mutually exclusive, so I just find the probability of each, add them together. That's how I get at least 1 ace. Find the 1 ace, 2 aces, 3 aces, all of them up to 7 aces. But notice this is a very hard problem, because each of those problems, exactly 1 ace, exactly 2 aces, exactly 3 aces, all those are binomial problems. So we have to do the binomial problem 7 times. So we don't want to do that way. We don't want to find the binomial formula 7 times. So the trick is to use one of the previous lectures formula, which is this formula. It says that if I look up the probability of an event and look at the probability of the opposite or the complement event, they're related by this formula. The probability of the event A is equal to 1 minus the probability of the complement of A. So for example, if the chance of it raining tomorrow is 40%, the chance of it not raining is 60%. It's just the opposite complement event. So we're going to use that trick to do this problem. So let A be the event of at least 1 ace. Instead of doing this problem, which is very hard, I'm going to do the opposite or complement problem, which is much easier. So what's the complement of A? So not at least 1 ace. So if I want the event that is not at least 1 ace, that means I want no aces. Right? At least 1 ace means 1 or more aces. If that's not true, then I have no aces. So the complement event is no aces. And notice this event is much easier to calculate. To get the event that we have no aces, we need the first row to be not an ace, and the second row to be not an ace, and the third row to be not an ace, all the way down to the last row to be not an ace. All these events are independent, so they're easily calculated, and because of the multiplication rule, we can multiply all of these because of the multiplication rule. So so there's no conditional probability involved. So the probability of the complement of A is, what's the chance of getting no ace in the first row? Well, 6 out of 7, because there's let's see, is that right? So the probability of not getting, no ace in the first row. I think I'm making a mistake here. So if I roll a die, the probability of not getting an ace is actually 5 out of 6. So sorry, I need to modify this, but it should be the chance of not getting an ace in the first row, it should be 5 out of 6, because in a die I have 6 outcome, and 5 of them is not an ace. So this should be 5 over 6 to the 7 power, because I want all those to be no aces. And so I'll have to fix that in my notes, so please look at my notes for that. And that means the probability of the opposite event is just simply subtracting that from 1 or from 100%. So notice the point of this problem is that to do the at least 1 ace problem, it's much better to do the opposite event. And so that's what we want. So that you're going to see some of that in workbook this week. Okay, thank you for watching.